In this tutorial, we will focus on determinant of matrix. Determinant. Determinant is a value associated with a square matrix. Determinant can be used to determine the inverse exists or not. In addition, determinant can be used to find the inverse. The determinant of A is denoted by this symbol or this symbol. Determinant of 1 times 1 matrix. For any 1 times 1 matrix A, here, the determinant of A is equal to the element of A. Please note that the matrix must be a square matrix. For examples, this is the matrix A. The determinant of A is 2. Here is another example. This is the matrix B. The determinant of B is -3. Determinant of 2 times 2 matrix. For any 2 times 2 square matrix in this form, the determinant of A is equal to A11 times A22 minus A12 times A21. Please note that it must be a square matrix. Here are some examples. We can use the above formula to calculate their determinants. Determinant of 3 times 3 matrix. For any 3 times 3 matrix A, here, the determinant of A is equal to this formula. We can remember this formula easily. Look at here. The formula is equal to A11 times A22 times A33 plus A12 times A23 times A31 plus A13 times A21 times A32 minus A13 times A22 times A31 minus A12 times A21 times A33 minus A11 times A23 times A32. We can try to use the formula to calculate the determinant now. Here is an example. The above formula has been used to find the determinant of A, which is equal to 0. Minor cofactor. We first introduce the terms minor and cofactor of an element Aij of a matrix A, where it is the matrix A. The minor of an element Aij, denoted by this symbol, is a determinant of order n-1 of a matrix obtained by deleting the I row and j column of A. Here is the minor of Aij. The cofactor of Aij is denoted by this symbol. The cofactor is equal to -1 to power I plus j times minor Mij. Here is the cofactor of Aij. Here is an example. We find the minor of the element on first row and first column. First, we need to delete the first row and first column. So we get this form. Then we use the formula of calculating determinant of 2 times 2 square matrix, and the minor is equal to -29. Then we find the cofactor by using the formula on the previous page. The cofactor of the element on first row and first column is equal -1 to power 1 plus 1 times the minor. Therefore, the cofactor is equal to -29. The similar steps for calculating the minors and cofactors of the other elements of A are shown below. Determinant of n times n matrix. Let A be a square matrix of order n. Here are the formulas of determinant of A. Both formulas with any I and j can be used to calculate the determinant. Here is an example. The formula on the previous page is used. There are 6 methods to find the determinant by putting I equals to 1, I equals to 2, I equals to 3, j equals to 1, j equals to 2, j equals to 3 respectively. You can use either one method to calculate. Here is another example. To find the determinant of A, we use the previous formula, and put I equals to 1. Since the second, third and fourth elements on the row 1 are all 0, it is easier to find the determinant by putting I equals to 1. Example 3. Let A be a 2 times 2 matrix. Use the formula on page 15 to find the determinant. The result is equal to the formula on page 7. Example 4. Let A be a 3 times 3 matrix. Use the formula on page 15 to find the determinant. The result is equal to the formula on page 9. You can try to do it once. Properties of determinant. Let A and B be 2 square matrices, with same order, and K be a scalar. Here are some properties. The first property, the determinant of A is equal to the determinant of transpose of A. Second, the determinant of the product of A and B is equal to the determinant of A times the determinant of B. The third property, if we interchange any 2 rows or 2 columns of determinant A, then the result becomes the negative of determinant of A. Next, if all the elements of one row or one column have a common factor k, then we can take this common factor out of the determinant. Next property, if all the elements of one row or one column are sum of 2 terms, then the determinant will become the sum of 2 determinants. Besides, if all the elements of one row or one column are 0, the determinant will be 0. If the corresponding elements of 2 rows or 2 columns are equal or in proportion, the determinant will be 0. In addition, if all the elements of one row or one column add the multiple of corresponding elements in any other row or column, the determinant will become unchanged. Last properties, let A be a square matrix of order n and K be a scalar. The determinant of K times A is equal to K to power n times the determinant of A. Here are some examples. The first property on page 24 has been used in example 1. The elements in row 3 are equal to -2 times the corresponding elements in row 1. Therefore, it becomes 0. The second property on page 24 has been used in example 2. the elements in column 1 plus 2 times the corresponding elements in column 3, does not affect the determinant. Thus, we get this, which is equals to example 1. And it is equals to 0. The last property on page 24 has been used in example 3. All the elements of a common factor 3 and the order is 3. Hence, it is equals to 3 to power 3 times this determinant. And this determinant is equals to example 1, which is equals to 0. Inverse. The inverse of a square matrix A of order n is denoted by this symbol. A times A inverse is equals to an identity matrix of order n, where the inverse of A is also a square matrix or order n. Before calculate the inverse, we first introduce the adjoint matrix. Here is the symbol of adjoint matrix and here is the formula, where the uppercase Aij is the cofactor of elements Aij. The inverse is equals to 1 over the determinant times the adjoint matrix. Here is an example. Refer to the example on page 13, we find the inverse by using adjoint matrix and the determinant. If the determinant equals to 0, the inverse does not exist. Otherwise, the inverse exists. Exercises. Here are some exercises. Try to do it now, and see how well you understand the topic. This is the end of the tutorial. Thank you.